Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at the chain rule. So the chain rule says dy dx equals dy du over du dx. Here it's sort of like the du's cancel out. Remember, du means change in u. It's an infinitesimal quantity. So if you cross out these two, you're left with dy dx. Now you might see the chain rule written like this. F of g of x. To differentiate that, you differentiate the function sort of as normal, and then you times by the derivative of what's inside. This chain rule is also called function of a function rule, and that helps us because it tells us when to use it. We use it where we have a function sort of inside another function. Both of these are saying the same thing. I just wanted to put them both there so you know what's going on. Okay, what does this all mean? Well, let's say we have y equals x squared minus 3 to the power of 10. So our normal rule for powers of x is that we move the power to the front. We're going to leave what's in the brackets alone, decrease the power by 1. So moving the power to the front, decreasing the power by 1 isn't new. What is new is that we need to times by the derivative of what's inside. So the derivative of x squared minus 3 is 2x. So we write that as 20x times by x squared minus 3 to the power of 9. See, with a function like this, if we were to expand it, that would take forever just to expand it. So we needed a quicker way here. What we've essentially done is we've said that this thing inside is u. See, u being x squared minus 3, that's a function of x, but then it's been raised to the power of 10. So that's actually another function of x. It's almost like we have a function and then another function here of x. So we actually follow this chain rule up here. So here, if u is x squared minus 3, this is our du dx, the derivative of y with respect to u. If y equals u to the power of 10 is 10 u to the power of 9. That's what we did there. All right, let's differentiate f x equals sine of x squared. So here we kind of have a function, sine, and then there's sort of another function here, the squaring function, x squared. So how are we going to go about differentiating this? Well, what we're going to do, we know the derivative of sine x is cos x, so we're going to change the sine to a cos, and we never change the argument. We never change what goes in the brackets. So now we have cos of x squared. So that part's sort of normal. What's new? We need to multiply by the derivative of what's inside the brackets here. And again, the derivative of x squared is 2x. So that's our final answer here. Again, it was kind of like u was x squared. Derivative of sine u is cos of u, because u is x squared. And then we need to times du dx. So if u is x squared, differentiating u with respect to x gives us that. All right, y equals e to the power of negative 1 over x. When you're differentiating e's, always keep the e and the power the same. They don't change. But what we need to do is multiply by the derivative of the power. So the derivative of negative 1 on x is actually 1 on x squared. So we can write it like this. If you're asked to write it with a positive power, it'll be 1 over x squared e to the 1 over x. Yeah, we're done. All right, let's now look at using the chain rule to differentiate functions involving natural log. So let's say that y equals natural log of fx. So using the chain rule, what we would do is we would let u equal f of x. So that means du dx, that means differentiating u with respect to x, will just be whatever the derivative of this function is. So if y equals ln of fx, if we've let this be fx, then we have another equation, y equals ln u. And so dy, derivative of y with respect to u, is just 1 on u. So using the chain rule, the derivative of this is that times that. It's f dash x times 1 on u. But of course, u was f of x. So that means here, the derivative is going to be f dash x over u which is fx. So if you're differentiating log of some function of x, the derivative of that function goes on top, the original function on the bottom. So let's differentiate this. Y equals natural log of x cubed outside 1 minus x squared. So clearly we have log of some function of x. Now, finding the derivative of the inside, that would be pretty tough. We need to use a few different rules. What we can do is make life easier on ourselves here using log laws. So what I'm going to do is rewrite this. We know that if you have the log of a product, it's just the sum of the logs. So because x cubed is being timesed by 1 minus x squared, I can rewrite it like this. Now that helps us. It's much easier to differentiate a sum than a product. Now also note we can use the log second power rule. So if we have log of x cubed, we can move the 3 to the front. So this will be 3 ln x plus, and we can do the same for the second one. Okay, let's go ahead and differentiate these. So I'll call that y dash. So we're going to leave the 3 alone. Now derivative of log x is 1 on x, so this will be 3 times 1 over x, or 3 over x. Now when we're differentiating log of 1 minus x, what we do is we put the derivative of what's in the brackets on top. Derivative of 1 minus x is actually negative 1, and then the function goes on the bottom. Now because this was a 2, we need to put a 2 now on top. We need to times the fraction by 2. So I'll change that to negative 2 over 1 minus x. So our final answer here is the derivative is 3 over x minus 2 over 1 minus x. All right, now we're just going to take a quick look at related rates. So the radius of a spherical balloon increasing uniformly by 2 centimeters per minute. At what rate is the surface area increasing when the radius is 5 centimeters? We're actually going to use the chain rule here to solve this related rates problem. So we're asked for what rate the surface area is increasing. We're actually finding how fast surface area, so I'll call that A, is increasing with respect to time. Now what we have here is we have dr dt. We were given that. We were told that the radius is changing 2 centimeters per minute. Of course, there's no reason these have to be equal, but we can use the chain rule to make sure they're equal. See, what I want is a t on the bottom and an a on the top. So if I times that by dA over dr, this is starting to look like the chain rule. The two drs cancel out, you're left with dA and dt. Okay, so I know this quantity, dr dt, so that's just 2, but what about dA dr? How do I figure that out? Well, we know that the surface area of a sphere is 4 pi r squared. So dA dr means I'm differentiating A with respect to r. So I'm just going to differentiate the r's. I'm going to move the power to the front. So 2 times 4 pi is 8 pi, decrease the power by 1. So dA dt is going to be 2 times 8 pi r. But we were told here that the radius is 5 centimeters. So I'm just going to quickly replace r with 5. So we get dA dt, 2 by 8 by 5, gives us 80 pi. And so that's about 251.33. Now, because everything was in centimeters, the surface area is in centimeters squared, and because it was per minute, our final answer will be 251.33 centimeters squared per minute. That's how quickly the surface area is changing, which we figured out using the chain rule. Alright, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.